Sorry about that. So welcome back to the section on functional encryption and even more. So our first talk is going to be certified, everlasting, secure, collusion-resistant functional encryption and more. And Rio is going to give the talk.
You hear me? Thank you for the introduction. I'm going to talk about the certified, everlasting, secure, collusion-resistant functional encryption and more. This is a joint work with Taiga, Fuyuki, Tomoyuki, Tapas, and Takashi. So in this work, we achieve functional encryption with certified deletion, and we also achieve compute and compare obfuscation with certified deletion, and we also showed its application to predicate encryption with certified deletion. But due to the time limitation, I focus on the first contribution in this talk. Okay, let's start with what is cryptography with certified deletion. So let's consider the following scenario. Bob wants to store ciphertext in the cloud server. And at some point, Bob downloads this ciphertext. And after that, Bob may want to delete the ciphertext from the cloud. However, the cloud server might keep a copy of the ciphertext. And it is impossible to prove that we delete information by using classical cryptography. However, if we use the power of quantum computation, it is possible that we prove that we delete information. So let's move to the syntax of functional encryption with certified deletion. The setup algorithm generates master public key and master secret key, like the standard functional encryption. And we also can generate functional decryption key for function f by using master secret key. The encryption algorithm is slightly different. This algorithm outputs a quantum ciphertext and also generate a verification key. We can decrypt the quantum ciphertext by using functional decryption key, and we can get f of plaintext. And we have a deletion algorithm, which takes quantum ciphertext and outputs a certificate for deletion. By using the verification algorithm, we can check whether this certificate is valid or not. So if the certificate is valid, it is guaranteed that the ciphertext is deleted. This is functional encryption with certified deletion. And let's see the security notion of this primitive, certified everlasting security. It is very similar to the standard security notion of functional encryption. The adversary is given the target ciphertext, and the adversary can send a key query and receive functional decryption keys. The different point is at some point the adversary output the certificate for the target ciphertext, and if this deletion certificate is valid under the verification key, then after that the adversary has unbounded computational power. And certified everlasting security means that even for this strong adversary, the ciphertext does not leak any information beyond the f of m. This is a notion of certified everlasting security for functional encryption. Okay. So there are many works on cryptography with certified deletion. However, all of them are about all or nothing type encryption with certified deletion. All or nothing type encryption means secret key encryption, the public key encryption, attribute-based encryption, and so on. We can recover entire plain text by using a decryption key. But we don't know whether we can achieve functional encryption with certified deletion and more other cryptographic primitives. In this work, we answer this question affirmatively. Okay. And the next, we move to what is the technical hurdle and what is our solution. So there is a very strong result about cryptography with certified deletion. Bartek and Krana present a general compiler for achieving certified deletion. this compiler takes cryptographic primitive X in this set and transform it into a primitive with certified deletion. So if we use public key encryption as an underlying cryptographic primitive, then we can obtain public key encryption with certified deletion by using this compiler. However, the question is whether this compiler works for FE or not. The answer is no. Why? So let's see the reason why the Bartek kernel compiler doesn't work for functional encryption. The compiler is like this. We use BB84 state by choosing Z and theta, which are lambda bit strings, and we encode it in quantum bit by if theta is 0, then we encode it in computational basis, and if theta is equal 1, then we encode it in Hadamard basis. And by using the underlying encryption algorithm, we slightly modify the encryption algorithm like this. We first generate the BB84 state, and we encrypt theta and mask the plaintext. The plaintext M is masked by computational base part of Z. And the verification key consists of Z and theta. This is transformed encryption algorithm. And the deletion algorithm takes this quantum ciphertext and measure BB84 state in Hadamard basis. And the resulting measurement result is a certificate for deletion. To verify this certificate, we check Z for all Hadamard basis part. The intuition is like this. If we measure BB84 state in Hadamard basis, then the information about computational base part disappears. So this XOR of computational base part works as an extractor and hide information about M in information theoretic sense. This is a Bartek kernel compiler. However, if we apply this compiler to functional encryption, we get F of masked plaintext. So we cannot obtain F of M if we directly apply this compiler to functional encryption. This is the problem. To solve this problem, we introduce the notion of public slot FE. This is almost the same as standard FE, but the decryption algorithm is slightly different. The decryption algorithm takes the ciphertext and functional decryption key and public input. And then this algorithm output F of plaintext and this public information. This is public slot FE. We can achieve this new primitive by using one-way function and indistinguishability obfuscation. And then we transform this public slot FE into FE with certified deletion. And let's see how to obtain FE with certified deletion from public slot FE from the next slide. So the idea is by using a public slot part, we unmask the plaintext. So the encryption algorithm is the same as the original compiler. This algorithm outputs the BB84 state, and we encrypt theta and beta. Beta is the masked plaintext, as before. And then we change the key generation algorithm like this. We consider function G, where F is hardwired in. And G takes theta, beta, and public input, and output F of XOR of computational base part of public information, and XOR beta. So if we use BB84 state as a public input, then we can unmask beta. We can apply this decryption algorithm in coherent way, so we can obtain F of M by using public slot FE. The functionality is OK now. However, there is a security issue in this construction because the adversary can obtain f of 1 minus m by using a different public input. Because the adversary can use any public input by using a public slot part. So this is a big security issue. We solved this problem by using a one-time signature. So we certify BB84 state by using one-time signature. We apply signature generation algorithm to the BB84 state and generate the quantum state psi. If theta j is equal to 0, then we can obtain zj, and the second register, we can obtain signature for zj. And if theta j is equal to 1, then we can obtain superposition of signature for 0 and signature for 1. And we slightly modify the function g in the previous slide. Now g takes theta, beta, and the verification key of one-time signature, and the public input, and the signature. Then this function g outputs the same value if signature is valid for public input part for all computational basis part. Okay, so then here, private part is theta, beta, and the verification key, and the public part is public input and signature. So, okay, so before I explain the intuition, verification algorithm is like this. Just measure this modified BB84 state in Adamada basis, and we check whether outcome satisfies this relation. So we can check the certificate is valid or not. Okay, so our compiler is this. The intuition of the security proof is like this. We cannot modify the public input part due to the unforgeability of one-time signature. So we can force the adversary to use valid computational basis part. So the adversary cannot get beyond f of m. And we can apply the Bartek-Kraner lemma to this construction. So we can achieve certified everlasting security by using Bartek-Kraner lemma. In fact, there are other subtle issues in security proofs, but due to the time limitation, I skip these subtle issues in this talk. Please read our paper for the data. And in this work, we also achieved bounded. So in that functional encryption with certified relation, we use indistinguishability obfuscation. However, if we consider bounded collision-resistant FE, then we can achieve certified derivation from standard public key encryption. And we also achieve compute and compare obfuscation with certified derivation from a standard LWE assumption. And we can show that we can use this compute and compute obfuscation to achieve predicate encryption with certified derivation. And this is achieved from the standard LWE assumption. Let me summarize our work. So we consider cryptography with certified derivation and beyond all or nothing type encryption. We achieve functional encryption with certified derivation and many other interesting cryptographic primitives. I also want to note that there is a concurrent and independent work which was presented yesterday. Bartek, Goyer, Kraner, Malavolta, Regis, Robert also achieve FE with certified derivation by using a different approach. That's it. Thank you.
Are there any questions? So please step up to the microphone. Okay, well, I have a question. So I'm not very familiar with this area, and I was wondering if you could give some intuition about this BB84 state, and why was that chosen, and if there's any other applications of your results regarding that state?
Okay, so BB84 state is very basic tool in quantum cryptography. So wait a sec. So there were if theta is okay, there were computational basis part and automatic basis part. So if the intuition like this, by using measure this BB84 state in either basis part, then the other basis part, the information about the other basis part will disappear. So that is intuition. And we also want to note that it is, in general, it is impossible to copy quantum state. And the BB84 state, in general, it's impossible to copy. So this is intuition of these two.
Okay, thank you very much.
Thank you.
So our second talk is going to be about lower bounds for lattice-based compact functional encryption, and the talk is going to be given by Akim Unal.
Thanks for the introduction. This is a joint work with Erkan. Yes, we're going to have some fun time for the next 20 minutes. What's an FE scheme? You should all know by now. This is the second talk and the second block. In case you didn't pay attention last 100 minutes, let me repeat. Super short. A symmetric FE scheme. We have our master secret key holder. This is a nice squirrel over here. And it can take a message and encrypt it with a master secret key to get a ciphertext and send it to a user or adversary, that's the eagle. And it can also use the master secret key and a function to derive a special secret key for this function f, and can also send it to an eagle. And the eagle now can take the secret key and the ciphertext, and with the decryption algorithm, it can derive the function evaluation of f on the message point. And we can repeat that. So squirrel can generate a new secret key for another function g, send it to an eagle. It can compute a new function value of g on x. And we basically want the following. That's what NCPA security guarantees. From this ciphertext and all the secret keys, the eagle does not learn anything more about the message x than the function values of the functions it knows on this point x. Okay, we have to talk about some technical terms, I'm sorry. Unbounded collusions. We want security under unbounded collusions. Means the eagle may ask for a lot of secret keys, which are polynomial but not bounded a priori. And as long as those secret keys cannot distinguish between the two challenge message pairs, they won't help at the NCPA game for the adversary. Another thing, linear FE or inner product FE is usually called IPE. That's just an FE scheme that supports secret keys for only linear functions. So our message space is set modulo p to the power of n. We can evaluate linear function in it. Yeah. And quadratic FE, that's one step higher. Again, with the same message space, but now we can evaluate quadratic functions. So we can issue secret keys for quadratic functions, modulo p over set p over n variables. All right. It's a good question. Why? Why are we even doing this? Like compact quadratic function encryption and lower bounds on top of that. Such a technical thing. Why even care, right? I'm going to give you two reasons. First one is obfuscation, of course. Always obfuscation. Here's the thing, we know a lot of different paths lead to obfuscation, but in reality they are all factorized over compact FE. And if you could get some interesting new compact FE schemes for, let's say, from lattices, could imagine that a part of this mess over here would simplify a lot. Second reason is pairings. So you know LFE gives us IPE, linear FE, but it probably does give us functional FE and quadratic FE. And it's interesting because we have all those things from pairings. So if you want to understand what are the limits of lattices in comparison to pairing-based assumptions, those results may be a good starting point. Okay, our results, we're going to reuse our framework. We're going to prove everything in our framework here. We're going to make a notion of what we think is a good less-based functional encryption scheme. We're going to prove lower bounds for less-based quadratic compact FE. They are not black box. They live in our framework, so you can always try to circumvent our results. But the good thing is they're agnostic to a concrete assumption. So you can use ring LLB, erase LLB. It should make a large difference, in my opinion. Yeah. So when do we call an FE scheme lattice-based? I want to require a few things. Ciphertext are vectors with a ciphertext modulus Q, the outer modulus of dimension m. Secret keys are polynomials over those m coordinates of our ciphertext, and they are of some constant degree. Decryption, that's quite simple. It's also really typical. We take a secret key polynomial, evaluate it on a ciphertext. That gives a value modulo Q. We round it down from a Q, or we scale down from a Q range to a P range, and then round it down to the nearest integer modulo P. And the encryption algorithm, I'm not going into details here, I'm sorry, but the encryption algorithm is offline, online of constant depth. Basically, it's simple. Offline phase may be very complicated, but online phase, once I see the message, I have to be very simple, of constant arithmetic degree. This captures most less-based schemes. In particular, decryption is quite normal. Encryption is a bit, but it doesn't capture everything. So FHE is not captured. Because FHE uses bit decomposition, we cannot capture this with offline, online encryption. Okay, so our theorem. Let's assume we have a lattice-based quadratic FE scheme, lattice-based in the sense like before, which is linearly compact. So ciphertext dimension m is linear with message dimension n, and secrets they are of minimal degree, which is degree 2. In this case, the scheme is either not NCPA secure or not correct. That's what we're going to prove. And we're going to use a tool. I proved this 4 years ago. You can find a nicer write-up in my upcoming PhD thesis in a few months. Let's assume we have a now secret key encryption scheme for messages over some large enough modulus P, such again, ciphertexts are vectors. Encryption is offline and online of constant depth. Again, technical term, not going into details here. Important, each ciphertext is of short norm modulo Q. In that case, if that's the case, then the secret key encryption scheme cannot even not be in CPA secure or not correct. Let me give some intuition, because again, technical, what does offline and online mean? It basically means there's no simple encryption scheme for a lot of numbers with short ciphertexts. That's the basic intuition here. And the nice thing is that the tool, this lemma here, even non-negligible correctness is not allowed. So the advantage of the adversary scales with advantage at decryption. And the nice thing is, decryption here, it doesn't even need to be efficient or even computable. This is a pure information theoretic result here. Okay. That's our hammer. That's how we're going to solve problems. And you know, when your tool is a hammer, you have to transform your problems into nails. So your thing on the right side, we know it cannot exist. Thing on the left side, we won't show it does not exist. We take our FE scheme and transform it into a forbidden SKE scheme. That's the whole idea. Yeah, now it gets technical, I'm sorry. How do we do that? First, I have to introduce something. We basically have to talk about a good function collection. We have a compact quadratic FE scheme, that's our starting point. And I want to put your attention to the following functions here. They're super simple. Those are just monomials, quadratic monomials for all ij, xi, xj. Those functions, they're supported by our quadratic FE scheme, because they're quadratic. So we derive now secret keys for each of those functions under some master secret key. And we require this. Those secrets are all degree 2 polynomials in a linear number of variables. And I want to put your attention to the following. This vector looks strange for some number x, x1, 0, 0, 0. But the important thing is, if I evaluate f1, 2 on it, then I get x. If I evaluate any alpha fij on it, I get 0. That's important. We have a turn off, turn on property here. I hope you remembered all of this if you're going to use it. So we are now going to construct our secret key encryption scheme on which we'll apply our hammer event. And encryption works as follows. We draw secret keys for each of those fij. We now use the old FE scheme, that's our starting point, to encrypt this vector x1, 0, 0, 0. We get a ciphertext CT from the old FE scheme. And now we do the following. We apply almost each secret key on this ciphertext except the first one. The first one is important, but all other ones are applied on it, and this is our new ciphertext CT prime. That's the ciphertext of our SKE scheme. This is secure. Why? Because we had collusion resistance, unbound collusion resistance. If I give the adversary with this ciphertext CT and all of those secret keys here, then the unbound collusion resistance that he cannot distinguish the X that's encrypted by CT from any other X, because all of those functions Fij, they need to vanish on this vector here. I didn't give you the important one. The important one is F12. You don't get it. You get every other secret key. So collusion-resistant NCPA security of FE scheme implies NCPA security in this context. And another nice thing is short, because we know how decryption works. Decryption works by applying the secret key on the ciphertext, scaling down, rounding. We know the value has to be 0. Again, we use this functions Fij for ij not 1, 2. So those things to get rounded to 0 modulo p, this polynomial evaluation needs to be smaller than q over 2p. So that's nice. Our less-based framework already tells us we are secure, we are short, we are almost done. Now we only need to decrypt, and then we're done. How do we do that? It's complicated. So if this wasn't technical enough for you, now it gets really technical. We're going to use an algebraic relationship. Yeah, algebra. OK. It's basically just very simple. We have a quadratic number of polynomials. Those are our secret keys. They are all of degree 2. And we have a linear number of variables. So our theorem from last year tells us they admit an algebraic relationship of constant degree. What's that? It's a polynomial h over new variables which represent the secret keys, such that h is non-zero. But if you plug in those secret keys as polynomials, h becomes the 0 polynomial, and the degree of h is polynomial is constant. That's what we want. And again, theorem last year proves such an h must exist. And our decryption algorithm is going to use this relationship h. It computes it, it knows the secret keys, it computes h. It plugs in everything it knows, so it knows CT prime, knows all the evaluations of the secret keys except secret key 1, 2, plugs them in. This yields a univariate polynomial in just one variable of constant degree. And now it computes a random root of g and outputs this scaled rounded down term here. And we know SK12CT, that's our payload, it has to be a root of G because H is an algebraic relationship. That's very nice. The second thing is, if you guess correctly, then this term here is just this term here. That's the decryption here, and because of correctness of our starting FE scheme, this must be X again, because F12 maps this strange vector over there to X. And we just carefully constructed this secret key encryption scheme and proved security and correctness. Now we're going to take our hammer and smash it to pieces. And because this is how we generate our contradiction. We start with something that we want to show can exist, and we construct something which we know shall not exist. Yeah, and we're done. I was way too fast. I'm sorry. Okay, so I'm going to spend a lot of time on open questions. So parameter restrictions were very strict, We required linear compactness, but what about relaxed compactness? What if the ciphertext size is maybe larger than n, or superlinear, but still subquadratic? What about that? And what if secrets are of any constant degree? And I looked at this exhaustively in my PhD thesis. And unfortunately, we're going to need new methods for this. With the QA methods, there's no way to prove a more general lower bound here. Also, people always ask me this, how can we circumvent this result? Good question. My best answer is use FHE, use bit decomposition. It's really not captured at all. This interests me a lot. What about if we use really small message modules p equals 2? Because here's the thing, our hammer, our tool, needs that the modulus is large enough, larger than some constant, which depends on the scheme. But if P is 2, then we cannot, this hammer's tool doesn't make sense anymore. So I want to give you a little puzzle or small challenge, and I hope somebody of you will solve it for me. Can we have a following? This is a simplified, minimalistic, function hiding IP scheme for message modulus 2. I call it a binary multiplication scheme because this makes sense to me. We have 4 key distributions, encrypt 0, encrypt 1, secret key 0, secret key 1. They're all output vectors. And if I have Oracle access to ciphertext of the 0-bit, I cannot distinguish between secret keys for a 0-bit and a 1-bit. If I have Oracle access to a secret key for a 0-bit, I cannot distinguish between ciphertext for a 0-bit and the 1-bit. But, and now here comes the correctness, if I have 2 bits A and B, and if I encrypt A and get a secret key for B from my distributions here, then the scalar product, modulo Q, it's small if one of the bits is 0, but it's large if one of the bits is 1. This encapsulates basically lattice-based function hiding IP, simplified down to the core, to minimal number of variables, 1, minimal modulus 2. I have no idea if this exists. Here's the thing, you can even construct an example with uncomputable distributions, enc0, enc1, sk0, sk1. It's fine. Even then, I have no idea if this can exist. I really don't know. So if somebody could solve this question for me, this would be great for me. And that's it. I'm 2 minutes too fast. I'm very sorry. But you have more time for questions. Thank you for your attention.
If anyone has any questions or a solution for the last slide, you can please step up to the microphone. We have a bit of time, so we can wait for the solution. We can go back to the slide.
Let me make a long drinking pause.
Drink fast. There's a question.
Hi, great. Thanks for the great talk. I don't have a solution for anything, but a question is that, so for pairing, we have these kind of schemes, and is there any way to kind of, you kind of prepared all these tools to aid your impossibility result, and the question is can we write down your properties in terms of pairings or like classical groups, and where does it work, and where does it it was kind of magical where all this magic. Yeah.
I think it doesn't work because I skipped over offline-online encryption. It's a bit complicated because offline encryption means I have an offline algorithm, enc off, over which I don't make any assumptions. It gets the master secret key, and then generates a bunch of correlated random polynomials. And then when I see a message, I can only evaluate those constantly polynomials at the message vector and output this as my ciphertext. I don't see maybe you could do this to pairings, but the problem is, let me jump back to my hammer. We need shortness here. This doesn't really make a lot of sense with pairings. If you look in the proof, I'm using one or more matrices a lot, and use that I can have good inverse of one or more matrices, modulo Q, so with short determinants. I think we need some kind of shortness. I don't know how much this has to do with lattices, but it has something. It has some geometrical interplay after it. And I also use a lot of statistics there at some point because I have to sample a lot and average to compute means. My guess would be it doesn't really work over group-based stuff, but good question.
Okay, that makes sense. So, do you think that you could show some primitive, it could be a very janky primitive that's impossible to construct, even if the encryption algorithm doesn't have this offline-online property, just using the shortness of the ciphertext?
No, because I can always take a ciphertext, do a bit decomposition.
Right.
Yeah. So this is kind of, so we really need offline-online because once you apply bit decomposition to your offline-online encryption scheme, it's not offline-online anymore because bit decomposition is so complicated. So yeah, if you want to circumvent results, bit decomposition is your favorite.
Okay, great. Thank you.
Thank you.
Are there any other questions? We can thank the speaker again. Great, so now we're at the last talk of our session, and it's going to be about succinct functional commitments for circuits for K-Lin. And the talk is going to be given by David Vu.
Great. So thanks a lot for the introduction. So I'm going to be telling you about succinct functional commitments, and this is joint work with Hotech. So in a functional commitment scheme, a user can commit to some input x, and later on open to an arbitrary function evaluated on the input x. More formally, a functional commitment scheme consists of a commitment algorithm, which takes as input a common reference string, the input x, and produces a commitment. Later on, there is an opening algorithm that takes in some commitment state, takes in a description of some function f, and produces an opening to the commitment to the value f of x. And finally, there's a verification algorithm that takes as input the commitment, the function, the purported value, together with the opening, and decides whether to accept or reject the committed value. The correctness property for the functional commitment says that if you commit to the input x and you open to a function f, you should be able to open to the value f of x. The main security requirement for a functional commitment scheme is binding, which essentially says that once I committed to an input x and I declared a function f, I should only be able to open to one particular value y. I should not be able to open a commitment to y0 and y1 with respect to the same function f. And finally, we have an efficiency property, which requires that both the commitment as well as the opening should be short. And by short, what I mean is the size of the commitment should be polynomial, only in the security parameter, and polylogarithmic in the length of the input. And likewise for the openings. So this should hold even if I'm opening to a very long value, the size of the opening should be only polynomial in the security parameter and polylogarithmic in the length of the input. So functional commitments actually capture many broad classes of functionalities, including many that you may have encountered before. For instance, it generalizes notions like vector commitments, where a user commits to a long vector and opens to a particular index within that vector. It generalizes notions like polynomial commitments, which corresponds to the special case where the user commits to a polynomial, say the coefficients, and opens to the evaluation of the polynomial at a particular point. And more generally, you should view functional commitments as essentially a way of constructing proofs on committed data. Namely, you have a user commits to some input x, and later on, the user wants to prove that the committed value satisfies some predicate. For instance, maybe that the committed value is a number between 0 and 100. This would be a range proof on committed data. So functional commitments give us a succinct way of proving arbitrary properties about committed data. And as such, these are very useful building blocks for constructing notions like succinct non-interactive arguments, or snarks. So because of its ability to give very efficient proofs on committed data, there's been an extensive body of literature studying constructions of functional commitments for restricted classes of functionalities and for general functionalities from a broad range of number theoretic assumptions, lattice-based assumptions, group-based assumptions, pairing-based assumptions, and many more. The first construction that constructed functional commitments for all circuits was a construction due to Libert et al., who gave a construction based on general purpose succinct non-interactive arguments, or snarks. And in the past year, there's been a proliferation of works showing how to build general functional commitments for all circuits from both lattice assumptions and pairing-based assumptions. In this work, I'm going to focus exclusively on functional commitments for general circuits using pairings or bilinear maps. And the reason that I'm going to focus primarily exclusively on bilinear map constructions is that these are the constructions that give you the best succinctness. So if you think about the context from zero-knowledge snarks, here, pairing-based constructions remain the constructions with the best concrete levels of succinctness, where the proofs only consist of a constant number of group elements. And so we can ask, in the setting of functional commitments, can we hope to construct a functional commitments that support all arbitrary circuits where the size of the commitment and the size of the opening only consists of a constant number of group elements? Namely, can we match the succinctness level of a general purpose pairing-based ZK snark, but without relying on any knowledge assumptions or idealized models? Turns out that there's actually a large body of work that has also studied constructions of functional commitments from groups with bilinear maps. Again, the first construction using general purpose snarks, you can instantiate it with the beautiful construction of Gross16, a ZK snark from pairings, to get exactly the asymptotics we care about. Of course, you pay any assumption you need, either some kind of generic group model or AGM type of analysis here. If we restrict our attention to constructions from falsifiable or more standard assumptions, then we have constructions based for special classes like linear functions, polynomials, and so forth. And two very recent works, one by Balbas, Catalano, Fiore, and Lai, another by Kalai, Lombardi, Vaikunthanathan, and Weeks, showed how we can build functional commitments for all circuits, either from a Q-type assumption or from the standard K-lane assumption. Of course, if we're focusing on constructions that have a constant size opening and a constant size commitment, neither of these constructions quite hit the mark. For instance, in the Balbas et al. Construction, the size of the opening scales with the depth of the circuit that's being considered, while the Kalai et al. Construction, based on general purpose batch arguments for MP, they have a construction where the size of the opening contains a polynomial number of group elements, but where the polynomial only depends on the security parameter. So our work gives the first construction of a functional commitment for all arithmetic circuits where the size of the opening and the size of the commitment only contains a constant number of group elements. It has a larger common reference string, scales with the fifth power of the size of the circuit. And in terms of assumptions, it's based on a standard bilateral K-linear assumption, essentially the assertion that the K-lane assumption holds when the challenge is encoded in both of the source groups. So just to give some perspective, this gives the first pairing-based construction that supports all circuits based on falsifiable assumptions, where the size of the commitment and the size of the opening only consists of a constant number of group elements. The previous constructions that had this level of succinctness relied on general-purpose ZK snarks for all of MP. It also gives the first scheme that only makes black box use of cryptographic primitives or cryptographic algorithms, where the size of the commitment and the size of the opening is only a polynomial in the security parameter. All previous constructions here relied on non-black box techniques, either, again, a snark or a batch argument for MP. And as an interesting implications of this result, so once we have a succinct functional commitment with this level of succinctness, we immediately get things like a snark for arithmetic circuits that has a universal setup and constant size proofs. Previously from pairings, we only had a construction that had a circuit-dependent common reference string. We can also use this to get a homomorphic signature that supports general bounded depth circuits, bounded size circuits, where the size of the signature contains only a constant number of group elements. And previously, again, the construction relied, pairing-based constructions had a dependence on the depth of the circuit. Okay. All right, so let me give you a brief survey of how we actually construct functional commitments for general circuits. And the starting point of our work is this really nice framework by Balbas, Catalano, Fiore, and Lai, where they've introduced this notion of a chainable commitment. So let me start by telling you what a chainable commitment is. So the syntax of a chainable commitment is I can commit to a vector of inputs. So here I have a k-dimensional vector that I am committing to. And I can produce some succinct commitment to this vector of values. And if you want to be concrete, I'm going to try and keep the algebra to a minimum in this talk. But if you want to think about what this commitment looks like, it's a Pedersen-style commitment, subset product in the exponent. This is the only slide I think with algebra in this talk. All right, so in a normal functional commitment, once I've committed to an input, I can now open to some value. In the case of a chainable commitment, I'm going to think about the function that I'm opening to as a vector-valued function. So it takes a vector as input, it produces a vector as output. So normally now I would open to a vector, but in the case of a chainable commitment, what I would open to is a commitment to the vector itself. So the commitment is again short. So I'm taking something short and opening to something short. So instead of opening to the actual values, I open to a commitment of the values. And the associated binding property says that once I've declared my commitment, I can only open to one output commitment. I cannot open one commitment and a function f to two different output commitments. So once I have a chainable commitment, let's say that supports quadratic functions, it turns out that this readily generalizes to yield a functional commitment that supports all circuits. And the way that we're going to do it is as follows. I'm going to take let's say my arithmetic circuit, and I'm going to arrange everything in layers. And if all of the gates in the arithmetic circuit compute quadratic functions, that means that if I look at the function from one layer to the next, is a quadratic function of the inputs. So what does the functional commitment look like? Well, the input is just a commitment to the actual input. This hasn't changed. What does the opening look like? The way I'm going to construct the openings is I'm going to first evaluate my arithmetic circuit on the input, compute the wire values for every layer, and I'm simply going to commit to all of the wire values within each of the layers of the arithmetic circuit. So the commitments will have sigma 1 prime, sigma 2 prime, sigma 3 prime, corresponding to the intermediate layers of the circuit. So now, what I know is that sigma 1 prime is a quadratic function of the values committed to in sigma, right? Each of these gates compute quadratic functions, and so I can actually just give a chainable commitment opening between each pair of layers. The opening for the overall functional commitment is going to be the concatenation of the commitments to each layer, as well as the chainable openings from one layer to the next. So if you look at this construction, immediately you can see that the length of the opening grows with the depth of the circuit. The number of layers corresponds to the number of commitments I need to give, as well as the number of openings I need to give out. So this doesn't quite meet our level of succinctness. We really want something that has constant size commitments, constant size openings. So we need to do something more. So what do we do? So the commitment in our scheme will be exactly the same as before, just commit to the inputs. And the opening is where things get interesting. Instead of committing to each layer of the circuit and then giving openings between every pair of adjacent layers, what we're going to do is we're going to concatenate all of the wire values together into one gigantic vector. So here the gigantic vector has the input values, has the intermediate values, and has the output values all stitched together. And I'm going to commit to this monolithic vector all at once. Okay, so instead of committing to each layer, I will now commit to the entire trace of the execution. Finally, we also have the output, where and this the verifier can compute for itself. It can just take the output values and construct the commitment. So if you look at this picture, there are only 4 commitments I've written on a page, right? There's the input commitment, there's 2 commitments to the intermediate layers. Why we need 2 will hopefully become clear later on. And there's also the output commitment. So if all of the commitments have constant size, let's say a commitment is just a single group element, then everything is indeed short. So the question is, how do we argue binding? That's where things get a little bit more hairy. So the first thing to observe here is that the binding proof does not work out of the box. If I look at the entire execution trace, this is not a quadratic function of the input, right? Could be an arbitrary arithmetic circuit, could be some very high degree polynomial of the input. But the only thing I know from pairings right now, or from bilinear maps, is how to check quadratic functions. We don't know how to check arbitrary functions. That's actually what we're trying to build in the first place, right? So we can't just apply a chainable commitment for quadratic functions here. We need something more. So the main technical tool that we introduce in this work is a notion of a projective functional commitment. This will be a tool that will be designed to carry out a particular proof strategy to actually reason about the construction I just described. So in a projective chainable commitment, what you can do is the following. You can take the common reference string for the commitment scheme, and you can embed within it a secret index j. And then there's a projection function that takes a commitment to a vector and projects it onto a commitment to a prefix of the vector. It projects it onto a commitment to the first j components of the vector. So I can project an input commitment. I can also project an output commitment. So in this case, the input commitment I project, I get a commitment to the first j components. Take the output commitment, I project. Here I get the first j plus 1 components. So normally, if I have 2 commitments, the notion of chain binding says something like the following. If I start with an input commitment, I can only open to one possible output commitment. That's what chain binding says. There's one input commitment, 2 possible outputs. The 2 possible outputs, if you can open to both of them, then they must be the same thing. In the projective chain binding, we're going to relax this property. We're only going to say that I can have 2 different input commitments, but if their projections match, then I can only open to 2 output commitments whose projections also match. Right? So I don't require that everything matches everywhere. I only require that the inputs match on the first j components. The outputs then must match on the first j plus 1 components. Okay? So this is the sort of the new notion of projective chain binding that we're going to use to implement our particular proof strategy. So let's come back to our construction. We have our input, we commit to the entire circuit trace, and then we have the output commitment. The security proof now essentially boils down to showing statements of the following form. For instance, I want to show that in this commitment to the entire circuit trace, the inputs are the same, right? I'm actually evaluating the circuit on the same thing that I committed to. I better check that, otherwise it's not clear what I'm proving, right? We'll also require properties like the gate consistency. which says that each of the intermediate wire values were actually correctly computed. This is actually a quadratic relation now because we have the entire circuit traced. We're not looking at the outputs or the intermediate values as a function of only the input. It's of the function of all of the previous wires that I've committed to. And finally, we want to argue that sigma 1 and sigma 2 actually commit to the same thing, and that the output matches. So these are the kinds of statements that we want to show. Let me show you how we can now stitch these things together to actually get a functional commitment that supports general circuits. So suppose the adversary produces a commitment to some input. And suppose the adversary also comes up with two openings. So sigma 1, sigma 2, sigma 1, sigma 1, 2 prime. Both these are commitments to the entire circuit trace. And then two possible outputs, sigma out prime, and two possible openings, pi and pi prime. So initially, if we look at these two openings, we have no constraints on what they can be. These are arbitrary commitments that the adversary chose. Right? We have no properties, no guarantees so far. So we better use these previous proof systems, these previous building blocks, to now impose certain constraints on what these values are. So let's look at the first constraint, which is the input consistency property. We're going to argue that the input commitment and sigma 1 and sigma 1 prime, they both agree on their input values. Namely, if I project the commitments to only the prefix of length k, then they actually agree. Right? So this corresponds to a chain binding property. Certainly, the input commitment agrees with itself, then the projected outputs must also agree. So projected outputs agrees means that if I project sigma 1 and sigma 1 prime to the first k components, they will agree. So now what I want to do is I've established that these two sigma 1 and sigma 1 prime, they agree on the first k components. I'm going to now propagate that to sigma 2 and sigma 2 prime. Right? I'm going to use the gate consistency check between the first k wires of sigma 1 and the first k plus 1 wires of the output, sigma 2. This is a quadratic function. Right? The next wire is a quadratic function of all of the previous wires in the circuit. And I've also established that sigma 1 and sigma 1 prime, their projections agree on the first k components. So now by chain binding, I can say that the output commitments, they must agree on the first k plus 1 components. And that's how we extend to argue that if I project the output commitments, now I get the correct value. And now I can rinse and repeat, right? I can argue internal consistency between sigma 2 to sigma 1. So sigma 2 I'm going to choose now as my output commitment. Sigma 1 I'll treat as my sigma 2 I'll treat as my input. Sigma 1s I'll treat as my output. Because sigma 2 and sigma 2 prime agree on the first k plus 1 components, I'm going to argue that sigma 1 and sigma 1 prime must also agree on the first k plus 1 components. So if we look at this picture, it's very similar to the picture we started with, except now the commitments agree on the first k plus 1 components rather than the first k components. So now you just iterate this process one at a time until you argue that all of these commitments actually agree on every single component. And at this point, if they agree on every single component, then the output commitment check says you can only open to one possible output. So, and if you're familiar with constructions of snarks for P or techniques using batch arguments for MP, these are very similar techniques implemented algebraically. Okay, so that's how we can use projected chainable commitments to actually construct a functional commitment for arbitrary circuits. So in the interest of time, I can't actually tell you how we actually build projected chainable commitments. I'll refer you to the paper for the full details. Here, I'll just give you a very high-level building block, a very high-level overview, and maybe if you read through the paper, you can see how it matches to the main bullet points here. So the starting point of our construction is this really nice proof system for proving memberships in linear spaces by Kiltz and Wee. And the basic scheme that we start with only supports openings to a fixed linear function. So functional commitments you can open to any function. So here we start with a fixed linear function. But you can extend to an arbitrary linear function very easily just by using multiple copies of the scheme and exploiting additive homomorphism. Okay, so now we can support arbitrary linear functions. Still not good enough. We want quadratic functions. We can extend to quadratic functions using standard linearization and tensoring techniques. So now we have a functional commitment that supports quadratic functions. Now we need to support projections. So to get a projective chainable commitment, we're basically going to embed the commitment in a vector space. The real commitment will lie in one space. The projected commitment will lie in a shadow subspace. If you're familiar with dual system constructions or dual system proofs, you can view the real components as sort of the normal mode and the projected components in the shadow subspace as a semi-functional mode. And this is how we implement the projective chainable commitment. And finally, everything we can actually prove from the bilateral k-lean assumption. This is basically the k-lean assumption where the challenge is encoded in both of the source groups. OK, so just to summarize, in this talk, I described a general approach for constructing pairing-based functional commitments that supports all arithmetic circuits, and with the property that both the size of the commitment and the size of the opening consists of a constant number of group elements. And as an open question, I think something that's very interesting is, can we get something with a shorter CRS? So I didn't say why we got an S to the 5 CRS size, unfortunately, due to the interest of time. But I think a very nice question is, can we get a construction with a much shorter CRS? So something that's linear or, let's say, quadratic in the size of the circuit rather than circuit size to the 5. And with that, I'll conclude. Thank you very much.
Any questions? So I actually have one question regarding actually the open problem that you stated on your slide. So can you give a short intuition as to why we have this 5 in the exponent and how hard it would be to lower the exponent while still keeping constant size for the other two?
Right. Good question. So the S to the 5 comes from the fact that we have to support quadratics. So quadratic gives us S squared. And then to get to basically, so linear functions, we need to have a quadratic size CRS because we want to have a bunch of cross terms for cancellations. And then to support quadratic functions, that usually gives S to the 4. And now we need to also support a basis. So that gives us a final power of S. So then that roughly gets you to S to the 5. I think a simple approach, or one possible initial approach for getting a shorter CRS, is to choose the components to not be completely random, but in a correlated way. For instance, if you can take this components in a common reference string to let's be like g to the alpha to some, like basically use the powers of tau type of construction, you can potentially get something like a cubic CRS rather than a S to the 5. But I think getting a subcubic CRS may be more challenging.
Okay, thank you. And I think we have one question.
Thanks, David, for your talk. I have a quick question. Can you comment on, like, does the scheme support succinct verification with preprocessing or?
Yes, good. So that's a great question. So the scheme does support fast verification. So basically, if you know the circuit that you're going to verify ahead of time, you can pre-process a short verification key. And then the online verification time is also polynomial only in the security parameter. And, well, I guess it's a constant number of pairing operations. Yeah, so poly lambdas.
Right, thanks.
Anyone else? Okay, well, let's thank the speaker again and all the speakers of the session.